Today we're going to talk about the military airworthiness standard for multi-core processors. But before we get to that, I figured it would be a good idea to do a brief introduction to where we were prior to the release of AA-22-01. And to that end, we're going to talk briefly about CAS 32A. So CAS 32A was a position paper that was released by an international group of certification authorities that was meant as an addendum to the guidance provided in DO-178C. As DO-178C predates the widespread adoption of multi-core processors, none of the guidance presented in that document really deals with the very unique challenges that comes about from utilizing multi-core processors in safety critical systems. So CAS 32A was released in 2016, and it added some additional considerations for the use of multi-core processors. This was an informal document, though, so recently there has been a new release both by EASA and the FAA. We stylize this as AMC 2193. EASA calls it AMC, FAA calls it AC. In this presentation, we'll just refer to it as AMC 2193. This formalizes the guidance that was presented in CAS 32A. Rapita provided some contributions to this process, but in reality, there's just some minor changes that have been introduced between CAS 32A and AMC 2193. So, from a high-level overview, CAS 32A introduced 10 different objectives that certification applicants need to address in order to get a type certificate for their multi-core processing platforms and software. These break down into subsets depending on which DAL level you're using. So all of the objectives are applicable to DALs A and B, with only a subset being applicable to DAL C software. There are two high-level planning objectives. These deal with your software architecture and verification process, as well as some information dealing with your the hardware platform that you're using. Then there are 4 resource usage objectives. These deal with identification of critical configuration settings in 1, the mitigation mechanisms for those critical configuration settings in 2, identification of interference channels in 3, and then verification of resource allocation and efficacy of mitigation mechanisms in 4. Software 1 deals with WSET testing for multi-core software. Software 2 deals with DCCC, or data and control coupling. Air handling deals with safety nets, and the accomplishment summary is really akin to a SAS in a DO-178C world. So diving into a bit more detail about each of these objectives, as I noted, planning 1 and 2 deal with specific multi-core aspects of your software and hardware elements. So these deal with identifying the number of active cores in your platform, which shared resources are available to the software, which cores are going to be deactivated, any types of dynamic features that will be enabled by a software or hardware. This could come down to dynamic allocation of tasks to cores at runtime, which both CAS 32A and AMC 2193 discourage. And from the hardware side of things, it could have to do with dynamic frequency and voltage scaling or clock gating, things like that can change the platform's behavior at runtime. Now, resource usage 1 and 2 deal with configuration settings or critical configuration settings. And what these are really any of the pin settings or register settings that define how the processor or the multi-core platform works at runtime. So you'll note here that there's a little asterisk on MCP resource usage 2, and that's because this objective deals with how mitigation mechanisms that would prevent inadvertent alterations to these critical configuration settings. It was kind of noted that when they formalized the guidance in CAS 32A that this isn't inherently a multi-core specific issue. This is something that you have to do regardless of if you're using a multi-core processor or not, and therefore have already been covered by AMC 2152 and DO-254. Resource usage 1, that one just deals with the identification of those settings. So resource usage 3, and 4, these deal with interference channels, which are platform properties that can cause interference between software applications that are running on parallel cores. They're not specifically the resource itself, like the interconnect. It's a property of the interconnect, like a coherency mechanism, or the bandwidth, or the serialization of transactions as they pass through the architecture of the interconnect. It also deals with the verification mechanisms, verification methods of addressing these interference channels, like which mitigation mechanisms are put into place and how you go about testing to ensure that they are there. And then resource usage 4 deals with identifying the limitations of your platform and ensuring that the software that is being hosted on it do not exceed their available allocation. Now, software 1 and 2, these deal with software aspects of certification, specifically worst case execution time testing and DCCC. So software 1 actually has 2 different methodologies that are presented in AMC 2183 for achieving this objective. And that has to do with whether or not the platform can be considered robustly partitioned. And this is a term that is kind of inherited both from the verbiage of DO-178C, which was then further expanded in DO-297, or integrated modular avionics, sorry. And what that means is basically that you can ensure that from a resource point of view, that no partition or software application, or however you want to call it, can consume more than its allocated share of platform resources, whether that's memory or processor cycles or anything like that, that there's some mechanism in place that prevents it from going above and beyond that. From a temporal point of view, it's a bit harder to ensure. And what that means is that your software is capable of meeting its performance and functional requirements in its intended final configuration. And when you have software applications running on other cores, now you have the interplay of interference there that can cause software applications to have much higher worst case execution times and therefore exceed their available budget. DCCC here specifically talks about the multicore aspects of data and control coupling. We have a whole webinar specifically on DCCC, so if that's something that you guys are interested in, I recommend checking that out. You can get a lot of information from our website for that. And then the final 2 here are pretty much what you would expect. Air handling deals with safety nets, assuming that the processor is going to misbehave, and then also the definition of mitigations and protection mechanisms that will prevent against that misbehavior. And then the accomplishment summary is essentially an addendum to a SAS or a HAS that you would get in DO-178C or DO-254. And what this is basically just outlining how you've gone through and satisfied each of these objectives. Sorry, I just saw that there is a question over there, and I'll answer that real quickly. RTOS, that has to do with real-time operating systems. That's what that means. Okay, so what are the differences between CAS32A and AMC 2193? So CAS32A and AMC 2193, like I said, are essentially the same. There was some formalization of the documents. Specifically, AMC 2193 talks about the dynamic allocation of software execution, and explicitly states that this is not something that you want to do, and that the only way you can do that is if you employ these allocation features that rely on these robust and proven limitations. And essentially what that means is that you have predefined schedules or operational modes that you can transition between at flight, not the type of dynamic allocation that you would get on a standard PC, where you have an operating system or whatever that decides which core an application runs on. That's not what AMC 2193 is saying here. The resource usage 2 objective was removed in AMC 2193, as I mentioned, saying that this is already going to be covered by DO-152 or AMC 152 or DO-254. And then finally, there's some additional clarifications explicitly stating, what a multi-core platform is. For example, does it include platform software? So that includes this RTOS, or real-time operating system, or HV, or hypervisor, which is a layer above the RTOS. Includes board support packages or any type of ancillary software that is needed for any host software applications that can to achieve its functional and performance requirements. It also references AMC 2152 for how to go about deactivating cores. And then finally, it explicitly states that simultaneous multi-threading or the use of a core's architecture to interleave tasks such that you have two virtual threads happening at the same time, that is explicitly excluded from the scope of this document as well. There are some exemptions that get noted in both of these documents as well. For instance, lockstep processors or processors that are essentially used as a multi-core platform, but each core is executing the exact same software using the exact same input. And the reason for this is to have some redundancy or robustness in your platform, so you can check your output to make sure it's doing what it's supposed to. These types of applications or implementations rather are not not covered by CAS 32A, that they're explicitly exempt. And additionally, any processors that have cores that are linked only by a conventional data bus, that means that there's not a very complex bus or interconnect between the two of them, but rather are talking through PCIe or some well-defined protocol. There's no shared memory in these. There's no shared CAS, no shared cache, and no coherency fabric that you have to worry about. And then finally, it also adds explicit exemptions for coprocessors. So these are processing cores such as those that you would find on a GPU, whose execution is explicitly under the control of the CPU core. So in this case, they're really just viewed as another resource, another platform resource that can be utilized by a core, just as you would treat any of the other things like the interconnect or the memory or a PCIe controller. Now, that being said, there are some situations in which you need to consider GPUs. For instance, if you had a general purpose GPU that is capable of autonomously running code and accessing memory and doing all that stuff outside the control of one of the CPUs. In that case, you have to consider that as an additional core that's capable of generating the interference that needs to be addressed in order to satisfy the objectives of AMC 2193. So in conclusion, for the comparison between the informal document, CAS 32A, and the formal document, AMC 2193, is AMC 2193 really just continues all the same fundamental concepts that are introduced in CAS 32A. Fundamentally, any project that was started using CAS 32A can transition to using AMC 2093 without really any difficulty. Finally, several things that were unclear or ambiguous in CAS 32A were made explicit in AMC 2183. Okay, so from here, we're going to springboard into what today's discussion is really about, which is AA-22-01. So AA-22-01 is the Air Force's military use of multi-core processors guidance document. And what this is an extension of Mil Handbook 516C. So this document here, this 516C, defines the certification criteria and methods of compliance for all sorts of airworthiness, from the hardware that goes onto the aircraft, the avionics, the everything you could possibly imagine. This covers the entirety of the aircraft. So section 15 is really what we're interested in, and that is the analog that we're comparing to DO-178C. This section deals specifically with computer systems and software, but just like DO-178C, does not include specific guidance related to multi-core processors. So AA-22-01, this was introduced in 2002, and again, as a supplement to the guidance that you'd already find in Mil Handbook 516C. And so what this states at the onset is that it provides the information that's necessary for the planning and implementation of multi-core processors in military aircraft, specifically to cover the airworthiness verification activities that are specific to multi-core processors hosting safety critical functions. So that's some aircraft function that is being implemented by the software on this particular platform. So a little bit of a background too on this. Again, AA-22-01 as the extension of 516C is really from my point of view, in an unrefined state. So it is in its documentation, it states that it's a draft and that it is set as a supplement to the individual criteria that's presented in 516C. So you can kind of see over here on the left-hand side a snippet of what AA-22-01 really looks like. There's some introductory text, but then there's this giant table of these criterion that link to 516C criterion. And these are essentially just additional elements that you have to consider as you're going through and trying to satisfy the 516C criterion. Each one of these deals with or presents the identifier, some additional standard language, which is basically the what, and then additional method of compliance language, which is how do you go about demonstrating that you've satisfied this particular addition or addendum to the 516C standard. And recommends that program offices incorporate this guidance into any of their certification bases for projects that are using multicore processors. So in general, the two documents do have a lot of similarities. Specifically, you can note here, this is an example pulled out of both AMC 2023 on the left and AA-22-01 on the right. So MCP Software 1 deals with WSET testing and making sure that your software is able to perform functionally correct and have sufficient time to complete their execution. And this includes doing robustness testing of the interfaces that the MCP software uses to interact with the hardware. AA-22-01 goes through and has several criterion that talk about the same thing, talking about meeting your requirements and making sure that you have sufficient time, testing the interfaces, and then making sure that you have you're meeting your timing requirements. So in general, most of the elements that are presented in AMC 2023 are covered by one or more criterion that's presented in AA-22-01. That being said, there are some differences between the two documents. So for instance, MCP Planning 1 of AMC 2023 talks about IMA, or Integrated Modular Avionics, which is formalized in DO-178C. There is no mention of IMA or anything of that type in the AA-22-01 document. MCP Planning 1 also talks about that robust resource and time partitioning. Again, this is something that's coming from DO-178C and DO-297. AA-22-01 does not discuss robust partitioning in any way. And then related to that, Software 1, if you look at the actual verbiage of AMC 2023, there's two methods of satisfying Software 1 that are dependent on whether or not your platform implements robust partitioning or not. There's no alternative software verification paths presented in AA-22-01 based off of this because, as I noted earlier, there's no mention of robust partitioning in AA-22-01. So in addition to that, CAS 32A and AMC 2093 really leave a lot up to the applicant to make the decision of how they want to implement things. AA-22-01, on the other hand, presents explicit system requirements that you won't find in the civil documents. So the first thing, this is kind of a higher level one, is AMC 2093 discourages the use of simulators or emulators to do your testing and verification, noting that they are much less likely to be representative of your platform and less likely to detect errors. Whereas AA-22-01, that have several different criterions that talk about verifying or qualifying your simulators and modules to do this work. So this one was particularly interesting, is that in AA-22-01, there is an explicit requirement that states that the lowest level cache is dedicated in its physical entirety to its respective core. While this is something that is typically done by default in most software, or most hard multi-core platform architectures, the second clause here is where things get a little bit interesting, and that states that all the higher levels of cache are dedicated to a core either in their physical entirety or the use of some software or hardware partitioning approach. Again, this is not something that you'll find in CAS 32A or AMC 2093. There's no requirement in either of those documents that cache partitioning be implemented. And finally, there's another criterion here that talks about throughput utilization, stating that the application does not exceed 90% of the platform's capacity. Again, there is no analog to this in AMC 2093. Applicants are free to set their own margins. Now, as I noted too, there are some pretty big scope there's a very large scope that AA-22-01 attempts to achieve that is not analogous to AMC 2093. AA-22-01 has much broader reach than what you'll find in either of the civil documents. Specifically, AA-22-01 talks about service history and software build processes and load processes, and all of those types of things you can either find in higher level documents like DO-178C or other DO documents, DO-254 or one of the ARP documents or something along those lines. You'll find them elsewhere, just not explicitly in the Multicore things because the Multicore guidance, because they're not specifically Multicore problems. So, in conclusion, AA-22-01 does recommend some specific system and performance requirements that neither of the civil documents require. So, again, that's that lowest level cache, that maximum throughput utilization. A large chunk of AA-22-01 has no direct analog in either CAS32A or AMC 2093. Again, those are going to be found in other civil guidance documents like DO-178C or DO-254. And then fundamentally, the guidance that's offered by CAS32A or AMC 2093 is applicable to the certification activities in the scope of AA-22-01. So trying to satisfy the objectives of AMC 2093 will help you satisfy some of the criteria that is spelled out in AA-22-01, not necessarily all of it. So there are some things that still require clarification. As I noted, AA-22-01 is a draft document, so there is not formalization of all of these things. Some things, will require some explicit questions to the certification authority to try to understand what they mean. For instance, there is an explicit requirement in AA-22-01 that says unused cores must be hardware disabled or deactivated. So depending on the multi-core processor, that could be very detrimental to the performance of the hardware without giving you any additional determinism as a result. For instance, we've noticed on a few processors, there's bus arbitration schemes or timeouts. So if you hardware disable some of the cores, what that will do is basically cause the cores that are active to have to wait on the deactivated cores timeout in order for their transactions to be processed by the bus. AA-22-01 also explicitly states that testing covers all known interference channels. So whereas if you look at AMC 2193, there is explicit carve out for interference channels that cannot affect the software, do not need to be mitigated against or verified. So for instance, if you identify a PCIe controller having a handful of interference channels associated with it, but your software is not using the PCIe controller at all, well, then you can note that those interference channels will not affect the software, and therefore you don't have to verify any mitigation mechanisms, don't have to test your software against them. There's no such explicit language in AA-22-01. So does that mean if you identify interference channels associated with these disabled resources that you still have to verify that your software is robust enough to not, have their timing affected by those interference channels? Again, these are questions that need to be addressed. And then finally, this one's a bit more abstract, and that's you can have this safety supporting software element. This is verbiage or terminology that's used by AA-22-01 and 516C that basically represents a software application or partition. This requires that you have to have a static assignment to a single core. This is similar to CAS32A or AMC 2093 that discourages the use of dynamic software allocation. However, what happens if you break one of these elements up into two independent partitions? Maybe one does I/O and one does some processing. So now can you allocate them to different cores, even though they are still essentially performing the same parent function, still implementing the same aircraft function that it was before, just now it's parallelized. So again, this is something that will need further clarification from your regulators. And here is where I'll pass it off back to Andrea.
Thanks, Dan, for a great presentation. For me, if you're currently working on or planning a multi-core project, we'd be happy to talk to you about MAC 178 solution to support your project. So if you want to get in touch, we'll be able to provide you more information. Also, Rapita is holding a 2-day multi-core face-to-face training course in Anaheim in Southern California on the 21st and 22nd of May. So if you want to delve deeper into meeting the challenges of multi-core certification, there's more information on the website, or if you email marketing@rapitasystems.com, I'll happily send you an email and more details. So moving on to our live Q&A session. As promised. Thank you to everybody who submitted some questions. We have a couple of questions that I'll put to Dan if he wants to join us again.
Sure. I'm here.
Okay. First question, Dan, how would you go about determining an application's resource throughout utilization?
Right. So what's essential to doing this type of work is the observability channels that are available on most multi-core processors. What these are hardware event monitors or performance monitoring counters. They're essentially little registers that you can read from that you can configure to count a specific event. So what that might do is it might let you know how many process cycles are utilized between two different times, or how many cache accesses are being made. So you need to validate these tools, make sure that they're counting what you expect them to, but essentially you use them while your software is running to gauge how much utilization of individual resources are actually happening. CAS 32A does state that, or AMC 2023 does state that identifying this utilization must be done in a worst case scenario. So one of the things that we do at Rapita is we typically try to gauge this while running software against interference generators, things we call rapid demons. So they are specifically tailored to exercise a specific interference channel as much as possible. So while you're running your software, you can have these interference generators going while monitoring these observability channels to identify how much of a particular resource is being utilized at any given point in time. You compare that against the technical reference documentation to determine the upper bounds that the platform is able to provide and make the assessment as to whether or not you are achieving that 90% throughput utilization maximum or not.
Thank you. Secondly, another question. What type of features in a processor, board, or RTOS should one look for that might help to satisfy these certification objectives?
Right. Again, observability channels are huge. So making sure that the processor that you're utilizing has adequate observability channels for you to measure the application under test, or if you're just trying to benchmark supporting software, things like that, having access to this type of performance monitoring capabilities is key. What comes with that then too is the need for a good and accessible documentation. It's really hard on some of these processors to identify these observability channels. Sometimes it's hard to get buy-in or get support from the silicon vendor themselves to help you gain access to them. For instance, I know NXP, in order for you to get information from these counters, you need to have the expanded support basically to help access these, because these hardware event monitors are actually implemented on the silicon as a way of debugging the software or debugging the hardware during development. So it's not typically something that you would get access to in a normal application code. Another thing would be options for mitigating interference. So from a platform point of view, talking about caches, NXP PowerPC architectures, I believe, allow you to partition an L2 cache. For instance, the T2080 allows you to hardware partition cache the L2 cache to individual cores. So that's one way of mitigating the interference channels associated with that. RTOSs also provide that. For instance, DDCI, their DOS operating system, allows for cache striping. So if your hardware platform doesn't support hardware cache partitioning, you can set it up in software such that you map certain elements in memory such that they only hit certain areas in cache, and that's only accessible by your core. So yeah, having those accessible and well documented, so that way when you prepare your artifacts or present your artifacts to the certification authority, you have enough evidence to convince them of their of your due diligence and the efficacy of the mitigation strategies.